Welcome back. This is video 2 of lesson 3.6. We're talking about multiplying matrices. And so for example 3, we're going to use the given matrices and then to evaluate an expression. So we've got matrix A. Matrix A is a 3 by 2 matrix. Matrix B there and matrix C are both 2 by 2 matrices. So there's some interesting things we can do. Okay, for the first one, for part A, we're going to do A times the sum of B plus C. So the order of operations is still applying here. We're going to add B plus C together and then multiply by A. And then for part B, we are going to do AB plus AC, where we multiply first and then add. And this is going to show us an example of the distributive property. If these two values don't equal to each other, then we can know that the distributive property definitely does not hold, but if they do equal each other, that's evidence toward the distributive property holding. Alright, so A times B plus C means we're going to do 4, negative 1, 2, 3, negative 2, 0 times the sum of negative 3, 0, 1, negative 2, plus 1, 4, negative 3, negative 1. So let's add first. So remember, you just do that element-wise. So negative 3 plus 1 is negative 2, 0 plus 4 is 4, 1 plus negative 3 is negative 2, and negative 2 plus negative 1 is negative 3. Okay, we don't need our parentheses any longer because we've done that addition. So now we just have multiplication. So we've got a 3 by 2 matrix times a 2 by 2 matrix, and so the middle numbers match up, so that's great. So we're going to end up with a 3 by 2 product matrix. So let's do that matrix multiplication. Now, on this slide, in this presentation, they go straight to the answer there. Okay, but I want you to stop, and I want you to actually go through and do the matrix multiplication. So pause the video and go through. You're going to multiply the first row of your first matrix times the first column of the second matrix, then first row times second column. Then you're going to do second row times first column, and second row times second column. On this one we have a third row, so now you're going to do third row times first column, third row times second column. So go do that, and then I'll talk you through what you should have done to get to that product matrix. Okay, welcome back. So to get the negative 14, that's taking the 4 and the 3 and multiplying each one of those by negative 2. So 4 times negative 2 is negative 8, plus 3 times negative 2, that's negative 6, and that's where you get the negative 14. 4 times 4 is 16, plus 3 times negative 3, that is negative 9. 16 plus negative 9 is 7. So now we're ready to move to the second row. Negative 1 times negative 2 is 2. Negative 2 times negative 2 is positive 4. 2 plus 4 is 6. Second row times second column, we have negative 1 times 4, which is negative 4. And then plus negative 2 times negative 3 is 6. Negative 4 plus 6 is 2. Okay, and now we're going to go down to that third row. 2 times negative 2 is negative 4. Plus 0 times negative 2, well, that just adds 0, so negative 4 is the total. Now, third row, second column, we have 2 times 4 is 8, plus 0 times negative 3, 8 plus 0 is 8. So that's how they got that product matrix. If you're still a little iffy about the matrix multiplication, you might want to go back to the previous video and look at example 2 again. Also remember that after you do the problems to try on your own and you come into class, we will go over them. Alright, so on this next one we need to multiply AB plus AC and then multiply AC and then add them together. So here you go, you can see we've got matrix A times matrix B plus matrix A times matrix C. So we're going to do that whole row by column process for each of these. So let's see. So 4 times negative 3 is negative 12, plus 3 times 1 is 3, so that gives us negative 9. 4 times 0 is 0, plus 3 times negative 2 is negative 6. Negative 1 times 3 is 3, plus negative 2 is 1. Negative 1 times 0 is 0, plus negative 2 times negative 2 is 4. 2 times negative 3 is negative 6, plus 0 times 1 is 0, so negative 6. 2 times 0 is 0, plus 0 times negative 2 is 0. And so our last element in that first product matrix is 0. Now let's do A times C. So 4 times 1 is 4, plus 3 times negative 3 is negative 9. 4 plus negative 9 is negative 5. 4 times 4 is 16, plus 3 times negative 1, so that's 16 plus negative 3, that gives us 13. Negative 1 times 1 is negative 1, plus negative 2 times negative 3, that's negative 1 plus 6, so that's 5. Negative 1 times 4 is negative 4, plus negative 2 times negative 1, that's 2, so negative 4 plus 2 is negative 2. 2 times 1 is 2, plus 0 times negative 3, that's just going to be 2 plus 0, so 2. 2 times 4 is 8, plus 0 times negative 1 is 0, so 8 plus 0 is 8. So now we just need to add these two together. So negative 9 plus negative 5 is negative 14. Negative 6 plus 13 is 7. 1 plus 5 is 6. 4 plus negative 2 is 2. Negative 6 plus 2 is negative 4, and 0 plus 8 is 8. And the cool thing is you end up, if you look here, you have the same answer when you did A times B plus A times C as you did when you did B plus C and then times A. So the distributive property does hold for matrix multiplication. In fact, let's talk about properties in general. Let's see. Oops, there we go. So let A, B, and C be matrices and K be a scalar, so just a regular number. The associative property holds for matrix multiplication. If you want to multiply three matrices together, A, B, and C, you can do B times C and multiply by A on the left there, or you can do A times B and multiply by C on the right, but you can't change the order in which they are written. Okay, you can't say ABC equals CBA, and we'll talk about that in a second. The left distributive property and the right distributive property hold. You can do A times B plus C, because that's going to equal AB plus AC. That's what we just showed. You can do the right distributive property. You can have A plus B times C, and you're going to have AC plus BC. But notice that C remains on the right of A and on the right of B. Just like in the previous example, A stays to the left. You can't change the positioning. Associative property of scalar multiplication means K times AB is equal to K times A times B, or A times K times B. Notice that I keep saying, okay, you can't move things around as far as the positioning of A and B relative to each other. If A is on the left, it has to stay on the left. That's because there is no commutative property in matrix multiplication. AB does not equal BA. Okay, because AB means you multiply the rows of A times the column of B. BA means you multiply the columns, the rows of B times the columns of A. So you're using different rows and different columns to get the products. So AB does not equal BA. Order matters. I always like for you to see examples, real-world examples of why we're doing what we're doing. Matrix multiplication is useful in business applications because an inventory matrix, when multiplied by a cost per item matrix, results in a total cost matrix. So inventory times cost per item equals total cost. Okay, let's look at an example of that. Going to be our last example for today, and then you'll be ready to do the problems to try on your own. Okay, so 2 hockey teams submit equipment lists for this season as shown. Each stick costs $60, each puck costs $2, and each uniform costs $35. Use matrix multiplication to find the total cost of equipment for each team. All right, so to begin, we're going to write the equipment list. I don't know why it's not showing the picture, but you have the information on your note sheet there that the women's team needs 14 sticks, 30 pucks, and 18 uniforms. The men's team needs 16 sticks, 25 pucks, and 20 uniforms. So to begin, we're going to write the equipment list and the cost per item in matrix form. In order to use matrix multiplication, set up the matrices so that the columns of the equipment matrix match the rows of the cost matrix. Okay, so we want the columns of the equipment matrix to match up the rows of the cost matrix. Okay, so that means since we've got a cost for sticks, pucks, and uniforms, those need to be the rows of our cost matrix. So that means those need to be the columns of our equipment matrix, which means the rows would be women's team and men's team. All right, so for our equipment matrix, again, we want the columns to be sticks, pucks, and uniforms. And so the rows would be, there's going to be a women's team row and a men's team row. So just like it says in your table, you want that to be reflected in your matrix. Women need 14 sticks, 30 pucks, and 18 uniforms. The men's team needs 16 sticks, 25 pucks, and 20 uniforms. Our cost, you're going to list in order to match up the order of the column. The columns of the equipment matrix. So you want since the first column is sticks, you want the first row in your cost matrix to be sticks. Since the second column in your equipment matrix is pucks, you want the second row in your cost matrix to be pucks. And since the third column is uniforms in your equipment matrix, you want the third row in your cost matrix to represent uniforms. So each stick costs $60, so we have $60 in the first row there. Each puck costs $2, so we've got $2 for the pucks, and uniforms are $35, so we've got $35 for the uniforms. Okay, and this is really cool. Let's write out our matrices that we're going to multiply together. First, let's check the dimensions. The total cost of equipment for each team can be found by multiplying the equipment matrix by the cost matrix. The equipment matrix is 2 by 3 and the cost matrix is 3 by 1. Those threes match up, so their product is a 2 by 1 matrix. Okay, so here we've got our equipment matrix times our cost matrix. So if you look, when we do the multiplication, those 14 sticks that the women need, we're going to multiply by 60. That gives us the total amount to spend on sticks, plus those 30 pucks that they need times the $2 per puck, plus the 18 uniforms they need times the $35 for the uniform. And when you do that multiplication in addition, you end up with $1,530. So that's how much money needs to be spent on equipment altogether for the women's team. For the men's team, when we multiply our men's row in the equipment matrix times the cost matrix, the only column there, you have 16 times 60, so they need 16 sticks at $60 a piece, plus they need 25 pucks at $2 a piece, plus they need 20 uniforms at $35 a piece, and they end up with $1,710. So the labels for the products matrix are shown below. You've got total cost in dollars, and the first entry there is the women's team. The second element is the men's team. So the total cost of equipment for the women's team is $1,530, and the total cost for the men's team is $1,710. Okay, guys, y'all are ready to do the problems to try on your own. You need to try all of them. Okay, even if you don't get them all finished, try them all, and we will go over them in class next time, and then we'll get you started on your round so you can get plenty of practice. I'll see y'all later. Have a good day.